All right, good afternoon, good morning, good evening, good night, depending on when you're watching this video. In this video, we will be working through the exercise given on slide 31 of lecture set number 9. Okay, so this exercise is an example of a dependent two-sample hypothesis test. There are two sample hypothesis tests that we study in this course, the independent two-sample test and the dependent two-sample test. So in this illustration, we have a study of factors affecting milk production in cows was conducted on a dairy herd. One part of the study involved 8 randomly selected cows being fed their usual diet for a month, then a new diet for the next month. The average milk production in liters under the two diets is given below. Okay, so you can see here, the table is giving us an identifier for the cows. So the cows are cow 1 through cow 8. So we have 8 different cows. For 1 month, they are given the usual diet, and you can see that the milk production is reported for each cow. So for example, cow number 1 on the usual diet produced 39 liters of milk. On the cow number 2 on the usual diet produced 32 liters of milk, etc. And then on the new diet, we have the same variable. So on the new diet, cow number 1 produced 46 liters of milk. Cow number 2 produced 41 liters of milk, etc. Part A says, is there evidence that the average milk production increased on the new diet at the 5% significance level? So this is a fairly standard question, and it's a logical question given the scenario. We want to know, will the cows produce more milk on this new diet compared to the usual diet? Now, to answer this question, we first have to identify what kind of data we are working with. In this illustration, we have 8 different cows, and each cow is being fed 2 different diets. So this is an example of what we would call a paired data set, because each cow is giving us 2 values. So these 2 values, for example, for cow 1, the values associated with the new and the usual diet, they are dependent in the sense that they are both given for the same cow. So we have 8 observations, each giving us 2 measurements. So this is an example of a natural dependence. So this means that in order to answer this question, we have to run a paired two-sample t-test. Now, in setting up the test, there's actually quite a bit of work that has to be done before we actually run the test. So this includes assumption checking and actually computing the differences, which can be done in 2 different ways. Okay, so let's start off with the assumptions. That's always a logical place to start. Actually, you know what? We should start off with the construction of the differences and then do the assumptions, because it'll make more sense. Okay, so I'll call this preliminaries. So there's one main thing we have to do, which are compute the differences. Okay, so we have to compute the differences. So whenever we're working with paired data, we take the raw data as it's presented. So for us, the raw data is given in this table, and we essentially build a set of differences, and we operate on those differences directly. So really, what a paired t-test is a 1-sample t-test where there's a setup step that you use to compute the differences. Now, we can compute our differences in either direction. We can take the new diet values and subtract the usual diet values, or we can take the usual diet value and subtract the new diet value. The direction that you go doesn't really matter, but it's easiest in the case of a directional test, which is what we have here, to try and phrase the hypothesis test exactly as the question is phrased. So in this question, it says, is there evidence that the average milk production increased on the new diet? So the logical thing to do here would be to take the new diet values and subtract the usual diet values, because then we can ask, are the differences bigger than 0? And this would reflect the question in a fairly natural way. Again, you could take the usual diet and subtract the new diet values and then ask if those values are less than 0. That would be the exact same test and it would work out to give the exact same answer. So the direction in which we compute the differences is very important because it actually determines how the alternative hypothesis is going to be set up. So let's try it. Let's try and keep this very consistent with how the question's being asked. So I'm going to call my differences di, right? So I'm going to have 8 values here that I call di. Okay, so those are my differences. So d1 is going to be 46 minus 39, which is 7. d2 is going to be 41 minus 32, which is 9. d3 is going to be 39 minus 41, which is negative 2. d4 is going to be 47 minus 46, which is 1. d5 is going to be 35 minus 27, which is 8. d6 is going to be 29 minus 33, which is negative 4. d7 is going to be 35 minus 31, which is 4. And d8 is going to be 39 minus 32, which is 7. Just making sure I didn't make any mistakes. Okay, so these are now the differences. And what's going to happen here is we are going to perform a hypothesis test on these differences. So really, again, what we're doing here is once we have constructed the differences, and the direction that we do this does matter. Once we have constructed these values, we are simply running a one sample test on these values. Okay, so we're going to need 2 quantities. Well, 3 quantities, actually. We're going to need the number of differences. So this is little nd. Okay, so the second thing we're going to do is compute little nd, x bar d, and little sd. Okay, so these are the number of differences, the mean of the differences, and the standard deviation of the differences. But all 3 of these values are going to be computed in the ways that we discussed way back in the second week of the course, right? So the mean of the differences is the mean of those 8 values. So we just add them together and divide by the total. The standard deviation of the differences can be constructed using either the defining formula or the computing formula for standard deviation. Okay, so ND, there's really no computation here. This is just the number of differences. So that's simply 8. X bar D is the sum from I equals 1 to little n of each DI divided by ND. Okay, so this is going to be 7 plus 9 minus 2 plus 1 plus 8 minus 4 plus 4 plus 7. Okay, and that'll be divided by 8, and that should give us 3.75. All right. Okay, so now what we have to do, actually here, no, it's fine. I'll just leave it like that. So that should give us 3.75. Okay, now what we have to do is compute the standard deviation of the differences. So this can be done in 2 ways. We can use the defining formula or we can use the computing formula. The computing formula is a bit faster, so we'll use that. So we're going to have the sum from I equals 1 to n of each difference squared minus the sum I equals 1 to n of the differences all squared divided by the number of differences over the number of differences minus 1. Okay, actually, and sorry, this is the variance. So we're going to square root this after. Now, this formula is exactly the same as the computing formula that we used in lecture set 2 when we first introduced standard deviation and variance. The only difference here is I'm just replacing the usual x with a d, just to represent that I'm taking the deviation of the differences. All right, so to compute this, we need a couple of different quantities. So for example, the sum from I equals 1 to n of di squared is going to be 7 squared plus 9 squared plus -2 squared plus 1 squared plus 8 squared plus -4 squared plus 4 squared plus 7 squared, which is equal to 280. Okay. So again, the same idea. I'm just squaring each difference and adding them together. I also need the sum of the di. Okay, so this, I've actually written out the process for doing this above. I just didn't give the number. So that's just going to be the 8 differences added together. Okay, and that works out to be equal to 30. All right, so then here, I'm going to have 280 minus 30 squared divided by 8 over 8 minus 1. And when I work this thing out, I should end up with 4.892. Or sorry, I should end up with 23.929. So then the standard deviation is going to be the square root of the variance. So that's the square root of 23.929, which is 4.891. Or sorry, 4.892. All right. Okay, so now we have the differences, and then we have the 3 summary statistics that we need in order to perform the hypothesis test and build the interval. Okay, so there's quite a bit of work that goes into the setup. And the most important part of this is making sure we remember the direction in which we compute the differences, because that determines the direction of the alternative hypothesis in the case of a directional test, which is what we have here, because we are asking, is there evidence that milk production increased on the new diet? So our differences were all computed as new minus usual. So we are going to be asking, is there evidence that the population mean of these differences is bigger than 0? All right, so now we can actually start the test. So we start off with a set of assumptions. And again, this is essentially the same setup as a 1 sample t-test. All right. So first, do we have a random selection of differences? Well, the question tells us that we have 8 randomly selected cows. So if the cows are randomly selected, the differences will be randomly selected as well. So this first assumption is fine. The second assumption would be that X bar D is normal. All right, well here, we don't know if this is true. Okay, we only have 8 cows, and there is no information given in the question about the distribution of milk production. So we would have to verify this using a normal probability plot. Okay, so we don't know if this is true until we check using a normal probability plot. Okay, 3, we would say sigma D known. So the standard deviation of the differences, is that known? And it is not. We're only using sample values. But that's not a problem. That just means it's a t-test. And in the case of independent, or in the case of 2 sample hypothesis testing and confidence interval construction, we'll always be using t-tests. So this is the norm. Right? Maybe I can fit this up here. I cannot. Okay, so now we can start the hypothesis test. And the hypothesis test here is going to run the same way any of the hypothesis tests we have used in the course are going to run. So we start off with the null and alternative hypothesis. So as I had mentioned before, a paired two-sample t-test is actually just a one-sample t-test, but it's applied to those differences. So to the 8 values that we calculated in our preliminary step. So our null hypothesis will be, in almost every situation, the mean of the differences equals 0. And then what we have to determine is the direction of the alternative. Now, in our case, we are asking, is milk production increased on the new diet? We took new and subtracted usual in our calculations. So if milk production has increased, all of these values or the population of these differences should be bigger than 0, right? So if the milk production increased on the new diet values should be bigger numbers than the usual diet values. If we take a bigger number and subtract the smaller, we have a positive number, so a value greater than 0. So here, we're going to have mu d bigger than 0 because we took new minus usual. If we had done usual minus new, our alternative hypothesis would be mu d less than 0. So the direction that the difference is computed is very important because it determines the direction of the alternative, which we know is important because that determines where the rejection region and the p-value are located. Okay, on step 2, we simply state the significance level. I believe we're using the standard here. So we have alpha 0.05. Okay, on step 3, we compute our test statistics. So you'll notice that this is exactly the same as a test statistic for a one sample t-test. So 3.75 minus 0 over 4.891 divided by the square root of 8. And that gives us 2.168. Yeah, 2.168. Okay, now on step 4, we can take either the critical value or the p-value approach. And these are going to work exactly the same as they did when we were running them in the one sample case. Because again, what a paired t-test actually is just a one sample test applied to the differences. All right, so we are running an upper tail test at the 5% significance level. So we are going to have a t-value on 0.05, and our degree of freedom here is just going to be the number of differences minus 1. So we have a degree of freedom of 7. All right, so our critical value is on 0.05 and 7. All right, so if we go to the table, we have 0.05, 7, 1.895. All right. All right, and then we can see that our test statistic, 2.168, this is going to get into that upper rejection region. So we have evidence to reject the null, which means that there's evidence that milk production did increase on the new diet. All right, if we take the p-value approach, we will have the same answer. As always, just a reminder that you don't have to do both. I just show both so that you have examples of them. Okay, so here we're going to sketch out our student t curve centered at 0. Now we're going to mark down the test statistic. Okay. Upper tail tests are the easiest test to write p-values for because they are direct calculations. So we have the p-value is the probability that t is greater than 2.168. So we can go directly to our table. We don't have to consider any symmetry rewriting. Okay, so we have 2.168. Okay, so that's in between 1.895 and 2.365, right? So our p-value is therefore between 0.05 and 0.025. Right? Upper tail tests are very nice and clean in that sense. So we have, since 0.025 is less than this probability, which is going to be less than 0.05. Okay, then 0.025 is less than the p-value is less than 0.05. All right. So hopefully, as you can see, outside of that setting up portion, this is exactly the same as a one sample t-test, right? All of these steps are analogous to what we saw in lecture set number 8. The only difference is recognizing that we are operating on those sets of differences, which we have to construct once we identify the data is paired. Okay, so then on step 5, we have to make our decision, right? So if we have a critical value, we would say reject H0 since test statistic is in rejection region. And if we use the p-value, we would say reject H0 since the p-value is less than alpha. Right, so in this case, going back, alpha is 0.05. Our p-value is smaller than 0.05 based off of the statement that we found in step 4. So therefore, the p-value is smaller than alpha because it's smaller than 0.05. So we can reject H0 based off either approach, which we know is correct because the approaches will always agree. And now we will say if the normality assumption can be verified, then the data provide sufficient evidence to suggest that average milk production increased on the new diet at the 5% significance level. All right. So very similar idea to what we had in the one sample case. Again, or in this statement, I've added in a note that we have to verify that normality assumption, which we can do by constructing a normal probability plot for the data. Okay, part B asks, will a 90% confidence interval for mu d contain 0? Explain and verify. Okay, so first off, let's just make a couple of notes here. So if we're going to be doing an interval, we have to check the assumptions. I'm just going to write this out first. So here we can just simply say C part A, because they're the same set of assumptions. Okay, so now for the confidence interval, on step 1, we have alpha equals 1 minus 0.9, which is 0.1. Okay. So then we have T alpha over 2 comma ND minus 1 is equal to T 0.05 comma 7, which is the same critical value we used in the hypothesis test. So that's a critical value of 1.895. So this means that the interval and the hypothesis test are going to agree. Now, in the hypothesis test, we rejected the null. So what we have concluded is that there is evidence that mu d is greater than 0. Because the test and the interval are going to use the same critical value, the results of the test and the interval are going to agree. So we have evidence that the mean difference, mu subscript d, is bigger than 0. This means that the interval will give the same result, which means that the interval will give two bounds that are bigger than 0. So here what we would say is this confidence interval will give two bounds that are greater than 0. Therefore, the CI will not contain 0. All right, so now we just have to verify this. So on step 2, we're going to build the interval. So we have x bar d plus or minus t alpha over 2 n subscript d minus 1 multiplied by little sd over the square root of nd. So this is 3.75 plus or minus 1.895 multiplied by 4.891 divided by the square root of 8. So this is 3.75 plus or minus 4.892. I don't know why I keep writing 4.891. I just really want it to be a 1, I guess. 4.892 divided by the square root of 8, 3.278. All right, so then our interval is going to be 0.0472 to 7.028. Okay. So then we can say that this is verified. The CI does not contain 0. Okay. Both bounds are bigger than 0, so 0 is outside the interval. Okay, so those are an example. This is an example of constructing a hypothesis test and a confidence interval for paired data. Right, so we have to identify in this illustration that the data is of a paired structure. When data is of a paired structure, that typically means we have dependence. So once we know that there's a dependence between the two populations, so between, for example, the new population and the usual population, we have to run a paired t-test, which means that our first step is to construct the differences directly. The direction in which we compute the differences is very important, because if we are asking a directional question, so for example, is this variable larger than the other, or is this population larger than the other population, or is this population smaller than the other population? The direction that we compute the differences directly influences the direction in the alternative hypothesis. So here we ran an upper tail test, mu d greater than 0, because we constructed the differences as new minus current, and we were asking if there's evidence that the new diet produces leads to cows producing more milk than the usual diet. Right, so it's very important that we read the question carefully and identify the structure of the data, because that determines, again, the type of procedure we use. And once we've identified the procedure type, our process of running the test is very similar. There's just a little bit more of a setup because we have to compute the differences. You can, in this case, compute the difference in the other direction. So do usual minus new, and then just flip the sign in the alternative. So make it a lower tail test, and you will end up with the exact same result. Everything will just be on the negative side of 0. Okay, as always, if you have any questions, please let me know.